Okay, let's talk about Google's Willow chip, a quantum computer so powerful it's redefining the limits of computational possibility. Willow didn't just set new records, it obliterated them. It solved a problem in under 5 minutes that the fastest supercomputers on Earth would need 10 septillion years to complete. And here's the twist. Some scientists believe this quantum breakthrough might involve parallel universes, where calculations unfold across multiple realities at once. So, let's unpack what Willow has accomplished and why the multiverse is suddenly part of the discussion. Google's Willow has performed a computation in under 5 minutes that would take one of today's fastest supercomputers 10 septillion years. This astonishing figure surpasses all known time scales in physics and dwarfs the universe's age by a staggering margin. Not only that, but Google has also made an eyebrow-raising claim, saying that its new quantum chip may be tapping into parallel universes to achieve its results. In other words, Google claims its chip is so fast that its computations might have occurred across parallel universes, a bold assertion that has also sparked significant skepticism. So, what is the science behind this bold claim? Willow is Google's latest venture into quantum computing, a chip that harnesses the strange, counterintuitive principles of quantum mechanics to tackle problems beyond the reach of classical computers. If you're familiar with quantum computing, you've likely heard of qubits. A qubit, or quantum bit, is the fundamental unit of information in quantum computing. Qubits are created by manipulating quantum particles like electrons, photons, trapped ions, superconducting circuits, or atoms. Unlike classical bits, which are strictly 0 or 1, qubits can exist in a state of superposition, meaning they can be both 0 and 1 simultaneously. Think of Schrödinger's cat, which is both alive and dead until observed. But Willow isn't just about superposition. Google's researchers have made bold claims, stating that Willow can handle more complex problems with speed and efficiency orders of magnitude greater than anything we've seen before. And here's where it gets really intriguing: quantum error correction. For quantum computers to be practical, they must address errors, an issue classical computers don't face as much. The quantum states in a qubit are incredibly fragile, easily disrupted by heat, noise, or even cosmic rays, causing information loss. This is where quantum error correction becomes essential. Previously, the lack of error correction has been a significant obstacle to scaling quantum systems, but Google believes Willow has solved this challenge. With a new quantum error correction method, Willow could make quantum systems more reliable, enabling them to tackle complex problems and usher in a new era of computing. One of quantum computing's most exciting aspects is its ability to perform parallel computations. Thanks to superposition, qubits can exist in multiple states simultaneously, allowing quantum computers to process many possibilities at once. This could enable them to solve problems in moments that would take classical computers millions of years. Picture solving a giant puzzle. A classical computer would test one piece at a time, trying different combinations. A quantum computer, on the other hand, could test multiple combinations simultaneously, thanks to its parallel processing power. Now imagine taking this further. What if quantum computers didn't just process calculations in parallel but explored multiple possible outcomes simultaneously, rapidly identifying the optimal solution? That's the real breakthrough. With quantum error correction and a system like Willow, these calculations could be faster, more reliable, and more precise than ever before. Are we tapping into parallel universes? The ability to explore multiple possibilities at once resonates with the many worlds interpretation of quantum mechanics, a theory suggesting that every quantum event creates branching timelines of outcomes. While this remains speculative, Google's bold claim is drawing significant skepticism online. For one, the calculation Willow was designed to solve didn't have any immediate practical applications. The particular calculation in question is to produce a random distribution. German physicist Sabine Hossenfelder tweeted in response to Google's announcement, "The result of this calculation has no practical use." It's exactly the same calculation that they did in 2019 on a circa 50-qubit chip. At the time, Google made a similar claim, arguing that it had achieved quantum supremacy, or the point where quantum computers can do things that classical computers cannot, regardless of whether those tasks are useful. As John Preskill, who first coined the term in 2012, wrote in a 2019 Quantum magazine column, the implications and significance of Google's breakthrough remain up for debate. However, the company is already focused on the future, aiming to scale up Willow to a level where it could prove genuinely practical. I, for one, am very hopeful about Willow. What about you? Let me know by commenting below. While discussing parallel universes, here's a fascinating theory that is changing the way we see the universe. When looking at the universe on the largest scales using sophisticated telescopes, one thing becomes quite evident. Things are surprisingly simple and straightforward. Yet, when we look inside the universe using the Large Hadron Collider, even at the tiniest scales, everything aligns with established physics. No surprises. It's a strikingly orderly cosmos out there, from the colossal to the minute. Scientists thought two big ideas would explain everything. One is string theory, a massively intricate mathematical framework that, for all its flair, hasn't solved any major questions yet. The other is cosmic inflation, which suggests that the universe suddenly expanded faster than the speed of light for a fraction of a second after the Big Bang. But we aren't sure what came before inflation or what powered it. Together, these ideas suggest the universe is super complicated when you look closely and very chaotic on a macro scale. However, this doesn't coincide with observations. On the largest cosmic scales, the universe is both homogeneous and isotropic, meaning it appears largely the same no matter where you are or in which direction you look. It may be that the universe's apparent simplicity is due to the limited range of scales we can currently observe. As we explore much larger or smaller scales, the anticipated complexity our theories suggest may come to light, or maybe the universe really is as simple and predictable as it looks. If that's true, clues to cracking some of the universe's biggest mysteries might already be hiding in plain sight, waiting for us to connect the dots. What if the answer lies not in our universe but another? This leads us to Occam's razor. The simplest explanation is probably the correct one. For example, if astronomers observe unexplained lights on another planet, instead of concluding it's aliens, Occam's razor suggests simpler causes like atmospheric conditions. Why bring this up? Because many inflation models suggest that the early universe's rapid expansion should have created long-wavelength gravitational waves, ripples across spacetime. Detecting these waves would strongly confirm the inflation theory. However, refined searches have found no sign of these waves, narrowing the field and ruling out more inflation models along the way. Inflation theory does explain some issues, but it also brings challenges. For instance, what energy field powered inflation? Why were the specific initial conditions present? Some inflation models even suggest infinite bubble universes, raising philosophical and scientific questions about testability and challenging the nature of physical reality. Ignoring Occam's razor here would mean assuming no simpler explanations exist. Neil Turok, the Higgs Chair of Theoretical Physics at the University of Edinburgh, set out to change this. Together with his colleague, Turok approached a new theoretical model to address cosmic questions without relying on traditional inflation or string theory. By following Einstein's theory of general relativity backward in time, they reached that initial singularity, a point where space and time shrink to a single point. They proposed this singularity acts like a mirror in time. On one side, time flows forward, on the other, it flows backward. This mirror concept aligns with CPT symmetry, a fundamental balance in nature. To understand CPT symmetry, imagine the universe as a stage where particles act out a play. Charge swaps matter with antimatter, parity flips the scene like a mirror, and time rewinds the sequence. If you change all three at once, the laws of physics stay unchanged. However, the dominance of particles over antiparticles and the one-directional flow of time suggests CPT symmetry might be violated. The mirror universe concept reinstates this symmetry by suggesting our universe has a reversed counterpart. In this mirror reality, time moves backward and antiparticles outnumber particles. This parallel universe might not be a real place but a mathematical construct to explain symmetry at the universe's origin. Turok's team used this hypothesis to explain dark matter and neutrinos. They suggest heavy, stable right-handed neutrinos, which interact only through gravity, could be dark matter candidates. Observing how matter clumps across the universe might reveal clues about neutrino mass, confirming or refuting this theory. Turok's model also addresses why the universe appears flat and uniform on large scales, using the concept of entropy. They propose a rapidly expanding universe with a small positive acceleration as the most probable state. Density variations linked to inflation could be explained through quantum fields. More research is needed, but picturing the Big Bang as a mirror neatly explains many features of the universe. What do you think about the mirror universe theory? Is it here to stay? Let me know in the comments. If you enjoyed this, consider supporting the channel by becoming a member. Don't forget to subscribe.